Yeah. So coming to today, we'll just get started with the frequency domain solvers. So I'll cover up until frequency domain solver only. So coming to frequency domain solvers, what we have in ESI SAML software like Visual SEM is MOM. MOM in the sense it's method of moments, and MLFMM it's multi-level fast multi-pole methodology. And then we have physical optics, which is for high frequency solving, or if you're going for a complex problem, you can go with that. FEM, it's a nominal method which is available in different tools, finite element method. And coming to time domain solvers with what we have, maybe we'll be discussing on the time domain on tomorrow part. But just as a name itself, I'm suggesting. So we have SEMTD, EPLTD. In that we have finite difference in time domain. And then high frequency solver we have, where we have to switch for PAM, SEM, HF. And similarly, hybrid solver. We have hybrid solvers in the sense based on the application. If you want to split solvers, even that is possible. You can completely split the problem into n number of parts, and you can solve like MOM PO and MLFMM PO, FDTD PO, and hybrid CFIE and EFIE solutions. So this is one thing what we have under ESI SEM1 as a solvers part. So I'll just go with the frequency domain solver. I'll just get started with the MOM. What exactly the MOM is all about? How exactly it computes the solution? How to provide the solution with MOM. So if you see, general frequency domain solvers uses IE formulations, that is nothing but integral equation formulations. So here also in the MOM solver, what happens is the integral equations will be computed with the method of finite element method. Either it goes for the integral equation solving or it goes for the finite element method. Finite element method in the sense you are trying to split up the problem into subparts in terms of meshes. You are dividing the complete problem into subparts, there in which you will be actually be eligible to completely solve the problem very fast by doing some computations. Coming to MOM, method of movements, it can be applicable for the antennas and the structures which are electrically small, ranging between 0.1 lambda to 10 lambda. So this is one of the major parameter what we have to analyze. So whenever you are getting started with your antenna, first thing what you have to analyze is, if you want to go ahead with the antenna implementation, you have to calculate the frequency first. So what kind of frequency you want to operate with, and then you have to calculate the wavelength of that particular design. Based on the wavelength, based on the frequency of operation, if your antenna size, you have to compare your antenna size in terms of wavelength. So if your antenna size is in terms of 0.21 lambda to 10 lambda, then you can go ahead with MOM solver, because MOM solver solves in a different methodology. So you can see the complexities also, how exactly it solves up. So this solver uses classic Gaussian elimination method. This is a mathematical method what will be used for the matrix computation. So generally for a structure, while analyzing n number of unknowns on the structure, the solver will be parallelized. So it will be solving the complete parts into parallel approach. So the resulting matrix and the right hand sides that can be stored on the disk. So resulting matrix and the RHS. RHS is nothing but right hand sides with which we'll be actually solving the problem will be stored into a disk, and then once the complete computation is done, after that we'll be actually analyzing them, we'll be solving it, and then we'll be getting the final result. So if you're going with MOM, basically the storage of your PC also matters up, because it uses some storage from the parallelized methodology, and it analyzes the complete design parameters with the storage. And we also have an option which is called as out of core solving. Out of core solving is, if you are going for out of core solving, it uses your internal storage. With the internal storage also, it stores up the complete samples into internal storage, all the result file, all the temp files. It completely solves it, then it will give you the final result. So we have two options in that. I'll show you while we are going with MOM, we can go with both the things. I'll show you how exactly we have to go about. So coming to time, what is the exact time required if you are going with this MOM? So if I'm going with MOM simulation, almost it takes n cube of memory for the simulation, and similarly it is directly proportional to n square time. So you can see the time required for the simulation would be n cube seconds, what we can say it, and similarly the memory required would be n square. N is nothing but number of unknowns. So whenever you're getting started with your antenna design, you'll be actually splitting up your particular antenna into unknowns. So based on your unknowns, actually you will be solving the particular thing. So if you're going for the examples of this MOM solver, you can go for dipole antenna and other electrically small structures. So basic antennas like dipole, monopole, and if you're going for some small antenna which is electrically very small in terms of wavelength, then you can go ahead with this solver. So how to choose between the solver is, this is one type of methodology. You have to choose between the solver, like 0.1 lambda to 10 lambda. If it is available, then we can go with this particular solver. Similarly, MLFMM solver. So MLFMM solver, as the name itself says, it's multi-level fast multi-pole methodology. So this solver is applicable for electrically large structures which are ranging from 10 lambda to 100 lambda. Earlier you can see for MOM we have got 0.1 lambda to 10 lambda. Here we are getting 10 lambda to 100 lambda. So this solver is mainly useful for the installed antennas analysis as well as radar cross sections, etc. So installed antennas analysis in the sense, for example, if you are incorporating your antennas on the top of aircraft, or else if you're incorporating your antennas on the top of submarine, you can actually solve it. How exactly this particular solver will solve the complete matrix is, it goes with the iterative solvers methodology. So we have three different type of iterative solvers: GMRS, Big Stab, and QMR. These are the three different type of iterative solvers which are readily available. By default, we'll be going with GMRS. So there's slight thin line difference between each and every iterative solver what actually you're using. So the MLFM actually reduces the solution time and memory when compared to MOM solver. How exactly it reduces it is, the main function of MLFM is to diagonalize the Green's theorem. So here the complete methodology goes with Green's function. So Green's function, it tries to calculate the complete diagonal matrix. It will try to calculate, expedite the faster results with the fast matrix vector multiplication. And then basically, if you are working with MLFM, it uses combined field integral equations, that is CFIE. So it's nothing but CFIE in the sense, it's nothing but combined field integral equations, wherein you will be involving your electrical field integral equations and magnetic field integral equations. So the simple equation of CFIE is nothing but alpha EFIE plus 1 minus alpha MFIE. So it's nothing but alpha is a factor. For example, if I put my alpha factor as 0.5, so exactly I'll be getting half contribution from EFIE, half contribution from MFIE. So here the n will be the number of unknowns in the design. The required solution time to reduce will be reduced to n iterations into n log n. So instead of n cube, now we have scaled it down to n iterations n log n. And the required memory for simulation is directly proportional to n log n. So instead of n square, now we are going with n log n memory. So this is how we'll be actually solving it. So we have gain horn antenna, RCS of UAV. These are some of the examples what you can go ahead with this particular solvers. So coming to PO and FEM solvers. So PO and FEM solvers are nothing but, the solver is an asymptotic high frequency solver, which is applicable for electrically very large structures between 100 lambda to 1000 lambda. For example, if you want to analyze a big aircraft, a big submarine, then you can go ahead with this particular PO solver. With the increase in the size, electrical wavelength size and the curvature, you have to go ahead with this particular PO methodology, where it uses physical optics. So optical technology will be used to analyze the complete structure analysis. So here the solution time is directly proportional to n, and even the memory is also directly proportional to n, but you will be using a higher end solver. Coming to finite element method, this method is useful for the antennas and waveguide applications. So if you are going for the basic antennas and waveguide applications, to model the complex structures involving various metal regions, you can go ahead with FEM results in terms of sparse matrix, system solved in sparse solver. So I've just covered until frequency domain part. So tomorrow we'll try to discuss on the time domain and the other unique features what we have in ESI Visual SEM software, whatever we have. So let us just get started with the design part. So sir, can I now is it fine, sir? We can go with design, right? No issue with the other things, right, sir?
No, that will be fine.
Yeah.
What about the student? Is it they have to start parallel, or first you are going to show one or two problems?
I'll show one, like I'll show the steps, sir. They can follow it.
Okay.
It's also fine. Otherwise, it's a basic steps only. I'll wait for at least like 1 minute or so.
If one or two problems, they will note down the steps.
Yes, sir.
In the notebook, and then they will start one small problems. We can give 10 or 15 minutes, small problems, yes, and then we can start the new one.
Okay, fine, sir.
Yeah. They should note down the steps first.
Yes, sir.
One more thing, is it all has software installed in the system? You can go ahead, sir.
Okay, fine, sir. So here, actually, I have a design document for a specific antenna. So always it's a better practice to start with understand the series flow, how exactly one or two antennas are working, just like sir suggested. So once you note down all the steps, you will come across with a procedure how to get started with. So we'll be giving you some time where you can actually get started with the application development, and then if you have any queries, you can post it in the chat box wherein with we'll try to provide you the solutions on that. Okay. So now let us just get started with the visual mesh. So I've taken a new file. So open a new file. So directly you can go for file new. Whenever you open ESI Visual SEM, right from the beginning first. Yeah. So here, whenever you're opening your Visual SEM, and then here you have to click on applications, you have to select mesh. So once you select mesh, then you can just click new file so that it will be opening your new file. So opening your Visual SEM software application, selecting your mesh window in order to get started with the mesh part, and then select new file in order to open this particular user interface. So we have got this. Now let us just go ahead with this particular design file. So here the example, whatever I would like to show it, it's a half wavelength dipole. Half wavelength dipole in the sense it's also called as lambda by 2. Why it is called as half wavelength dipole also I'll tell you. I'll show you some resources on that. So the complete length you can note down. You can get started with noting down. So you can see if the complete length of the antenna is mentioned as 337.8 mm. So this is after calculation. Okay, 337.8 mm. And its half